everybody. In this next video, we're going to keep working with fractions, of course, and we're going to start talking about factors and how to put our fractions in simplest form. So, for example, let's say I have something like 2 times 5 equals 10. Well, 2 and 5 are called factors. So they're the things that get multiplied together to give the final result. So we can use these factors to help us break down fractions and to write them in the simplest or lowest form possible. So factoring a number means writing the number as a product. So factoring just means to break it down like this. So break it down. And what we're going to do particularly is we're going to learn how to do what's called prime factorization. And that's when we write a number as a product, like I just said, but of only prime numbers. And a prime number is a number whose only factors are 1 and itself. So basically, it kind of can't be broken down any further. So some examples of prime numbers would be 2, because the number 2 is only 1 times 2. Another example would be 7, because 7 is only 1 times 7. Or another example could be 11, because our only breakdown is 1 times 11. So something that is not prime is actually called composite. Would be an example like the number 6, because 6 could be 1 times 6, but it can also be 2 times 3. So it has other factors besides only 1 and itself. Or another example here could be the number, let's do 25. So 25 is 1 times 25, but it's also 5 times 5. So 25 has another factor, the number 5, besides itself. Now, composite factors are great too. So composite numbers are great too. And that's fine. But when we're talking about breaking things down for simplifying, we usually like to do what's called prime factorization. So we basically break the number down as far as we possibly can into only prime factors that cannot be broken down any further. We don't so much care about the factor of 1 here because it doesn't change anything. Multiplying by 1 does not create a new number, for instance. Okay, so just a few examples of prime numbers. And also the number 1 does not count as being prime. So we have 2, 3, 5, 7, 11, 13, 17, and so on. Okay, so those are just some of the first few prime numbers here. So these are numbers that cannot be broken down any further. Notice I didn't include 4 because 4 is also 2 times 2. We talked about 6 already. 8 is also 4 times 2. 9 is 3 times 3. 10 is 2 times 5. 12 is 6 times 2 as well, and 3 times 4. 14 is 7 times 2. 15 is 5 times 3. 16, 4 times 4, 8 times 2, etc. So I just try to list the first few prime numbers for you. And the interesting thing about prime numbers is they actually continue on indefinitely. We can always find a larger prime number forever, for infinity, which is a really interesting idea. You would think that maybe at some point everything just becomes composite or some combination of other factors, but that's not true. There actually are infinitely many prime numbers, and they do get larger and larger. All right, so let's do some examples. So I want to write the prime factorization of 24. And what I'm going to do is take that 24 and I want to break it down into only its prime factors. And a lot of times what we use here is a tree. So I take that 24 and I'm going to think about just one factor pair. Doesn't matter which one you pick. So I know 24 has lots of different factor pairs, right? 2 times 12, 3 times 8, and so on, right? 4 times 6. Doesn't matter which one you pick. Obviously, we want to pick one without a 1. We want to do something different. So let's pick, how about 4 times 6? Doesn't matter which one you pick. And then you're going to take that 4 and the 6, and you're going to break it down again. So 4 is 2 times 2, and 6 is 2 times 3. Now, 2 and 3 are prime numbers. I cannot break them down any further. So these are my ending values on the tree. So this is a, you can call it a factorization tree. So our answer here is anything that's circled. So 2 times 2 times 2 times 3. Or you can also write this as 2 to the third power times 3, depending on how we want to write our final example. Okay, let's do another one. I'm going to do the same question. This time do 60. So I'm going to take that 60 and I'm going to break it down into a factor pair. So it doesn't matter which one you pick, you'll get the same answer whether you start with one factor pair or another one. So I'm going to use 6 times 10 here. And then I'm going to keep going. Well, 6 is 2 times 3 and 10 is 2 times 5. And I'm going to notice that these are all prime, right? I cannot break these down any further into anything useful. So our answer here is 2 times 2 times 3 times 5, or 2 squared times 3 times 5. Now we do usually write the numbers in order, although technically you don't have to because multiplication is commutative, but we typically do. Now, as a side note, I do want to show you, let's say you use a different combination here. So let's say instead you started with 5 times 12. Well, 5 is prime, so I can't break that down any further, but I can break down the 12. And 12 is 2 times 6. Now, 2 is prime, but I can break the 6 down into 2 times 3. So notice here that you're still getting that same factorization no matter which combination you use for your factor pairs. They're all going to break down the same way, which is really nice, which is why we really like these prime factorizations, because we know we have all the possible factors there when we go ahead and do that. All right, let's do one more. And this is a good one to maybe pause the video and try on your own, see if you can get it first. So I'm going to do 63. Okay, so for this one here, think about what your possible combinations could be. And again, there's more than one, which is absolutely fine. So some of you may recognize that this is 9 times 7. Well, 7 is prime, but 9 is not. 9 is 3 times 3. So I get here 3 times 3 times 7, or 3 squared times 7. You can again write it either way, just depending on how the question is asking for the final answer. And again, just one last time, if you use a different combination, so you may have noticed that you could divide this by 3, and then you'd have 3 times 21. And if you keep breaking it down, you're still going to get the same factors. So we still get 3, 3, and 7 as our prime factorization here. Again, which is really nice. It's always going to be consistent no matter which factor pairs you use. So this tree method is just kind of a nice, easy way to stay organized. Now, as you're breaking things down, the better you are with your multiplication tables and division, the easier this is going to be. So I do encourage you, if you struggle with your multiplication tables, to maybe try and practice them, maybe just a couple minutes every night with some flashcards, or keep a multiplication table with you. So something that helps you find those factors really easily, or those combinations. But we do have some common divisibility tests, which are sort of like little tips and tricks that you can use. So a whole number Okay, so a whole number is divisible by 2 if it is an even number. So if you don't remember what even number is, that means that the last digit is 0, 2, 4, 6, or 8. Okay. So if you have an even number, so for instance, let's say I have the number 12. 12 divided by 2 will always come out nice and even for our answer, and give us 6. So not even as an even number, but it will come out as a nice no remainder answer here. So this is an even number because my last digit is a 2 in this case, so I can divide this by 2. So it's divisible by 3 if the sum of the digits is also divisible by 3. Now, this helps particularly for large numbers that you're trying to break down. But we'll do a regular example. Let's do 12 again. Okay. So our two digits here are 1 and 2. 1 plus 2 equals 3. And notice that 3 can be divided by 3. So 12 can also be divided by 3. Let me do another example here. So how about 144? Now this is a hard one where you may not know this off the top of your head. So is this divisible by 3? I don't really know. But if I add up my digits, 1 plus 4 plus 4, I get 9. And because 9 is divisible by 3, so is 144. It will also be divisible by 3. So it will come out nice and even here. If you do your line division, you're not going to get a remainder. And a third divisibility rule is 5. And you're divisible by 5 if the number ends in 0 or 5. So for example here, something like 120 ends in a 0, so it is divisible by 5, or something like 1,555 is also divisible by 5 because it ends in a 5. Now, these are just a couple of them, so I think these are the most common ones. You can be divisible by 10 if the number ends in 0. So that's not a prime number, obviously, for 10, right? 10 is not a prime, but it's a very helpful one as well. So if a number ends in a 0, it's also divisible by 10, and that can be a nice little trick. Now, again, there are other divisibility rules as well. So there are rules for the number 4, the number 6, the number 9, but I don't know if they're as helpful, if I'm being honest. I think the most helpful ones are 2, 3, and 5. Those tend to be our very common prime numbers that we see a lot. So I would start with those first. But if you're interested in other divisibility rules, I encourage you to look at your text or look at different websites to see some of the other ones. But like I said, these tend to be, I think, the easiest to memorize and the easiest to work with. All right, so let's do one more example here. Okay, so this time I'm going to write the prime factorization of 252. Now, this is obviously a number that I don't know factors off the top of my head. This is quite a large number, but I'm going to use my divisibility rules. So if I go to my divisibility rules, I do see that 252 is an even number, right? Because it ends in a 2. So I know that I can divide this by 2. So I'm going to start there. Now, I do have some work to do here. I am going to have to do some long division. 2 goes into 2 one time, which is 2. If I bring down the 5, 2 goes into 5 2 times, which is 4. Bring down the 2, and 2 goes into 12 6 times. And it comes out even. So I can at least start by making this a little smaller, and I have 2 and 126. Now I know 2 is prime, so I can circle that, but 126, I got to see if I can keep breaking it down. I notice again that 126 is still even because it ends in a digit that is either 0, 2, 4, 6, or 8. So I'm going to divide by 2 again here. All right, so 2 does not go into 1, but it goes into 12 6 times. And 2 goes into 6 3 times. Okay, so this was 2 times 63. Now, again, hopefully 63 is looking familiar to you because it's one of our common multiples that we see with our multiplication table. But if it's not, you can go ahead and try some more divisibility rules. Now, this is not even because it ends in a 3, and it's definitely not going to work with a 5 because a 5 has to end in a 0 or a 5. But I can try my rule for 3. So I'll show you here that if I take 63 and I add up my digits, 6 plus 3 is 9. Well, I know that 9 is definitely divisible by 3, right? 9 divided by 3 is 3. So I know that this is also divided by 3. So if I'm not sure of a factor here, I'm just going to use my divisibility rules. And then, like I said, I know we've seen this already, but you can go ahead and just kind of keep going that way until you find something that you feel a little bit more comfortable with. And now 21 is 3 times 7. Again, hopefully you're recognizing that. And my final breakdown then is that 252 is equal to, let's see, I have 2 2s, I have 2 3s, and a 7. Okay, so we can use our divisibility rules to help us with these larger numbers as well. And again, check out your text or check out some online websites if you want more divisibility rules, but I think those are the most common and the easiest to use. Some of the other rules get a little bit tricky and kind of not really worth memorizing. So those are the 3 ones that I think are worth kind of remembering and kind of keeping track of. Okay, so let's go on to simplest form now. Okay, so first, fractions that represent the same portion of a whole or same value are called equivalent fractions. So basically they're equal. They have the same value, even though they maybe look a little bit different. So for example here, 1/2 and 2/4 are equivalent. Now we're going to be able to show this using numbers too, but you can also show it visually. So for instance, if I have 1/2, I'll just use a rectangle here. So here is 2 parts of my whole. I'm going to shade one of them in, so there's 1/2. But notice that it's also the same as 2/4. If I were to cut this in half again and make 4 pieces, I still see that 2 of them are shaded in. So visually, 1 out of 2 pieces shaded or 2 out of the 4 pieces shaded are the same value. It's the same piece. So these are equivalent fractions, right? They represent the same thing, even though they look different. So, I mean, drawing pictures is nice, but we don't want to always have to draw pictures over and over again. So there's different ways to also check for equivalent fractions and to verify them as well. Another way to see if 2 fractions are the same is to use what are called cross products. Okay, so to see if fractions are equivalent, we can do the following. Okay, so one is to draw a picture. And that's what we did on the other page. So we looked at 1/2 and 2/4, and we were able to see that it's all the same picture, right? So that was the example we just did. The second thing we can do is we can check the cross products. And cross products mean that we're going to multiply across or diagonally. Okay. If the same, then the fractions are also equivalent. So for example, if I do 1/2 and 2/4, I want to see if these two are equal. That's my question. So what you do is you multiply across. So I do 1 times 4, and I do 2 times 2. So 2 times 2 is 4. 1 times 4 is also 4. Obviously, these are equal. Yes. So here, the cross products are equal. So the fractions are also equal. They are equivalent. Okay, so that's another way. So your cross products are just multiplying diagonally. Let me do one more example there, just so you have a second one as well. Okay, so let's say I want to check, is 1/3 the same thing as 6/7? So I multiply this way. 1 times 7 is 7. I multiply this way. 3 times 6 is 18, right? These are obviously not equal. So since the cross products are not equal, then the fractions are not equivalent. Okay, so that's another way we can just quickly check to see, are these fractions the same? Obviously, we can draw the picture if we're more of a visual person. That can be cumbersome to try to draw pictures all the time. So we can quickly multiply across, see if we get the same values. But the third way is to really just see if we can put our fractions in simplest form. to see if they are the same. And that's really what I want to spend the rest of this video on, is what is simplest form and how do we put our fractions in simplest form, because we're going to use this technique all the time. We'll come back to cross products occasionally throughout the class, so we're not going to get rid of that idea either. But we tend to use the simplest form a lot when we're finalizing our answers for fractions as well. So this is something that we really want to spend time on. And this is why we also spent all that time on prime factorization. So let's go ahead and talk about this. So a fraction is written in simplest form, also called lowest terms. Sorry, guys, hang on. All right, sorry about that, guys. The puppy started barking, so I had to take a little break. So let's go back to this definition. So a fraction is written in simplest form, which is also called lowest terms. When the numerator and denominator have no factors in common except the number 1. And the number 1 is always present because we can always multiply anything by 1 or take out a factor of 1 all the time. So we're not worried about 1, we're talking about something different. Just as a side note here, so we also sometimes say reduced. The fraction is reduced. That's a little bit more older terminology, I know, but I grew up with it as well. So if you remember that term, oh, reduce your fractions, the fraction is reduced, it's the same thing. It just means that the fraction is in simplest form or lowest term. So that phrasing has sort of gone away a little bit more nowadays, but I just want to throw that in there because I know sometimes I still say it, or those of you who had this work a little while ago may have learned that word in school as well. All right, so how do we actually get things in simplest form? So what we want to note here, actually, I think we're just going to do an example. Let's just do an example. Okay, so what you want to do is you want to factor the numerator and denominator and cancel any factors in common to both. Now, when I say factor the numerator and denominator, there's different ways to do that. So I'm going to use the prime factorization. So I'm going to break both of these numbers down as low as they can go first and show you how that works. And then I'll also show you a little bit of a shortcut. So I'm going to start with 12, and I'm going to break this down. So 12 is 2 times 6, and then 6 is 2 times 3. So here's where that prime factorization is coming in. So 12 is 2 times 2 times 3. And then for 20, well, 20 is 4 times 5, and 4 is 2 times 2. So I get 2 times 2 times 5. Now, I do like to leave it in the sort of expanded form here, not in the exponential form. When I'm simplifying fractions, I find it easier. So I'm going to take that 12 over 20, and I'm going to rewrite it as my factors. And then what we do is we cancel factors in common, and it has to be a 1-to-1 ratio. So if it's something in the numerator or something in the denominator, we cancel them 1-to-1. So I have 1, 2 here and 1, 2 here. And then this is a different cancelization, 1, 2 here, 1, 2 here. So I get the final answer of just 3 over 5. Now, why can we actually cancel these out? And the reasoning is because if you think about it, I have 2 over 2 here, which is just a factorization of 1. And then even here, right, I have 2 over 2, which is just 1. So canceling out a factor of 1, dividing by 1, doesn't change anything. It doesn't change the problem. So that's why we can go ahead and cancel. All right. Now, as a little side note here, if you're pretty comfortable with your multiplication tables, and your factors, then you actually can do some of these a little bit faster. So instead of going all the way down to prime factorization, you may have already noticed that, hey, these both have a factor of 4 in common, right? Because 12 is 4 times 3 and 20 is 4 times 5. So that's another way to do it as well, particularly as you get more comfortable with these problems and with your multiplication tables. You may be able to find factors, not necessarily prime factors, but just factors in general much quicker. Let's do another example. So I'm going to bring in an x here, so I'm mixing things up, and I'll tell you that the x is not going to make a difference. We're just going to tack that x on at the end. I'm going to focus on the 42 and the 66. So I'm going to do it with prime factorization first, and then again, we can look at more of the shortcut way. So for 42, I'm trying to think through my factors here. So I have this as 6 times 7. And 7's prime, but 6 I can break down into 2 times 3. And then for 66, I have 6 times 11, and then 6 is 2 times 3. So what this becomes then is that 42x over 66 becomes 2 times 3 times 7x, and 2 times 3 times 11. So we're just going to let that x hang out in the numerator, and I'm going to cancel my factors in common here, and I get a final answer of 7 over 11x, or you can write it as 7x over 11. Those are both the same thing. Now, again, if you're noticing right away, if you're like, oh, I'm pretty good with my factors, I know that this is 6 times 7, and I know this is 6 times 11. So you maybe recognize that common factor of 6 right away, then you can go ahead and still cancel that out, and that is absolutely fine. Another way to do it, instead of kind of writing the factors like this, those of you who may be more familiar, you also can write it as division. So another way to do it that, again, you may have seen once you become really comfortable with these factors is to just divide it out. So instead of dividing it this way in fraction form, we can just divide it using the division symbol. 42 divided by 6 is 7. 66 divided by 6 is 11. So we still get that same exact answer. Let's do another example. Again, write in simplest form. So I'm going to bring in a negative now, so negative 10 over 25 here. Now, if you had two negatives, they would still cancel out, just like a regular division problem, but I just have one negative, so my answer is going to be negative. So I'm maybe just going to write that in just to remind myself, and then I'm going to go through my factorizations here. So I have 10 is just 2 times 5, those are both prime, and 25 is 5 times 5, which is also both prime. So 10 over 25 becomes 2 times 5 over 5 times 5. So one factor, 5 will cancel, and I have 2/5 left over. So my answer would be negative 2/5 then. Now again, just as a couple of different strategies or ways that you can do it. So you may have noticed right away without even doing the prime factorization that, hey, these both have a factor of 5 in them. I know that. I'm pretty comfortable with my division and my multiplication. So you could have just canceled those out right away. Or again, using different notation. A lot of times we'll write it like this. Oh, I see a common factor of 5 in common. I'm going to go ahead and divide that out. So that's another way that you can write and simplify your fractions. So you're more than welcome to use any strategy if the problem doesn't specify. And just as long as you can simplify and get to that lowest form, then that is great too. One thing I will note when using this strategy, sometimes you may have to do that process more than once. So maybe, for instance, I'm just going to do one more here. So maybe I have 24 over 40. And you're like, you know what? I don't really want to go through my whole prime factorization. I just want to try to get it done. So maybe you notice that these both have a common factor of 4. So I'm going to start by dividing them both by 4. 24 divided by 4 is 6, and 40 divided by 4 is 10. Now, you just want to be careful if you're using this strategy because you may not get the lowest fraction right away. If I look at 6 and 10, I also see that, hey, these guys also have a factor of 2 here in common. And now 3 and 5 have no factors in common. They're both prime, so we are done here. So again, you just want to be careful if you're using a different strategy for your factoring. If you're not going down to the primes, prime factorization will work well, cancel all factors. But if you're not going down to the primes, if you're using a different strategy, you know, like this or this, then make sure you double check your final answer. Did you get all the factors? So here, if I did 4 first, I may have missed the factor of 2. So I need to come back and divide by 2 again to get that final answer. Okay, so just some different strategies on how you can get that simplest form here. Maybe we should just do one more example. All right, let's do a hard one here. 18x squared over 6x cubed. So you can kind of think of this in 2 different ways. If you want to work with the numbers separately and then the variables separately, you can do that. This could be a great one to maybe just use that prime factorization so we don't have to worry so much about, okay, did we get all the factors? So I'm going to go ahead and rewrite this using my prime factorization here. So 18 is 2 times 3 times 3. And then 6 is 2 times 3. Now, x squared, think about that. That means you have 2 x's. So that would be x times x. And x cubed means you have 3 x's. So x times x times x. And this strategy actually still works for variables as well. So I cancel my numbers in common, but I can also cancel variables in common. So here I have 1 pair of x's, and here I have another pair of x's. And you just want to be careful because it gets a little bit messy. So I have a 3 left up top, and I have an x left down bottom. So my final answer here is 3 over x. Okay, so we can still use this same process if I bring in some more variables. And then also, notice here I had an improper fraction, right? I had 18 on top and the 6 on bottom. It still works. It doesn't matter if I have an improper fraction. It doesn't matter if I have variables. I can still use the same canceling technique and breaking things down. So again, prime factorization is a great strategy because you know you'll always get all the factors in common. So I don't really have to worry about double checking my final answer. But if you want to do one of the other strategies, that's okay too. And as you get more comfortable with your multiplication and your division, then I think these other strategies are going to become more common for you when you just start dividing out the common factors right away. Okay, so one last example, kind of coming back full circle here into determining if 2 fractions are the same. So determine whether 16 over 40 and 10 over 25 are equivalent by writing them both in simplest form. Okay. So this was that third thing. So remember a couple of pages ago in our notebook, we were talking about, go back here, how do we tell if fractions are the same? We can draw a picture, we can do cross products, and then the last thing I said is that we can put the fractions in simplest form to see if they're the same, see if they match. And we kind of now know how to do that, so let's see that strategy in action. So for 16 over 40, so for this one here, I'm going to go ahead and break it down. So I'm going to do 16 is 2 times 8, and then 8 is 2 times 4, 4 is 2 times 2. And then for 40, I have, let's see, 5 times 8, 8 is 2 times 4, and 4 is 2 times 2. So I'm using prime factorization here. So 16 over 40 becomes, 16 is 2 times 2 times 2 times 2, and 40 is 2 times 2 times 2 times 5. So I see that this one becomes 2/5. Now for my second fraction, I'm going to use a different strategy because I'm pretty comfortable with 10 and 25. I know they're both divisible by 5. So I'm going to go ahead and just use this strategy instead. 10 divided by 5 is 2, and 25 divided by 5 is 5. So notice that since these are the same, then 16 over 40 and 10 over 25 are equivalent. So a third strategy to decide if two fractions are equivalent is you can put them both in simplest form and see if they match. If they don't match, then they're obviously not the same. But if they do match in simplest form, then you also have the same fraction there as well. So for this this video here, we went through quite a lot of things. So let me just kind of quickly recap what we've talked about. So we started out this lecture talking about how to find factors, right? So what factors are, what a prime number is. If a number is not prime, it is called composite. And then we spent the first part of this video really focusing on how to write things in prime numbers using prime factorization. So how to use those trees to break down our different numbers. We also talked about some of the common divisibility tests. So if you're getting stuck, checking to see if things are divisible by 2, 3, or 5 is usually a good way to start. If those numbers don't work, obviously you can try other prime numbers. So a number may not be divisible by 2, 3, or 5, but you can try 7, you can try 11, 13, etc. So you just keep trying something until you see if you can find another number. If you've tried everything and you can't find any more factors, then that number could itself be prime as well. So that's just kind of a little tip here is, let's say you have a number you're trying to break down. I always say start small. Try 2 first, try 3, try 5, kind of go up through the line until you can't try anything else. Then we also talked about how to tell if fractions are equivalent or basically the same. Do they have the same value? So you can draw a picture to see if they're equivalent, which is nice, but it can get a bit tedious. A quick way to check if fractions are equivalent is just to check their cross products and see if they match. But another way to check if fractions are equivalent is to reduce them to simplest form. And this strategy here, we're going to be using a lot in the next few videos. So to go in simplest form, the main way you can do it is to just go ahead and to use prime factorization on the numerator and denominator, and then you can cancel out your factors in common. As you become more comfortable with that, you can make it a little bit faster for yourself. So if you notice a factor in common that it may not be prime, but you know that it's common to both, you can just kind of jump right to that part and cancel that out right away. And we talked about using the division notation instead here. But again, you just want to be careful and make sure that if you are not going right down to prime factorization, then you just want to check your final answers to make sure you haven't missed any factors. And we can also apply this to to improper fractions and variables as well.